And so here's an example, but what was the general gist of these? We're going to need an equation that brings together different rates of change. Don't read, listen. Don't read, listen. Okay? We need an equation that brings together these two or more rates of change. And where is that equation with those different rates in it going to come from? This is the key to solving these problems. Where is that equation that has the multiple rates related together? Where's that going to come from? Do you remember? This was the big point on, is that Wednesday? Yeah. Do you remember where that's going to come from? Yeah, Charlie. Perfect. Did you see that? So we're going to start with, we need a quantities equation. Specifically, which quantities? The quantities for the rates that we're relating, right? Okay? So this is kind of in a nutshell, this is what these problems are like. We've got to figure out what rates we're going to relate, and then we kind of think backwards and think, okay, what are those associated quantities and how do those relate? That's how we start, and then we can derive the related rates equation from that. So here's a question. After spherical balloon is untied, it expels helium at 150 inches cubed per minute. How fast is the radius changing when the balloon has a volume of 50 inches cubed? So here's a more detailed roadmap that I recommend for these. First, let's identify all the rates involved. Okay, so whether they're known or unknown, whether we know what the value is or not, what are the rates involved? So what is one rate involved here? It says it expels helium at 150 inches cubed per minute. Is that a rate or an amount or an accumulation? That's a rate. Okay? So that 150 inches cubed per minute is a rate. It's a rate of change of what quantity? Yeah. Yeah, it's inches cubed per minute. So this is volume, right? So this is volume. Okay, so we'll keep that in mind. And then it says how fast is the radius changing? So that's what rate of change of radius. So those are our two rates that we got to relate to each other. Rate of change of volume and rate of change of radius. Okay, so this should be the easiest step of all then. What are the quantities for those rates? So we talked about rate of change of volume. So what quantity is key there? Is Kyle the only one who knew that? If it's rate of change of volume, then what's the associated quantity? Volume. And if it's rate of change of radius, what's the associated quantity? Radius. Okay, so let's assign variables. So, turn the thing on. So we're going to assign, so we can call V the volume. So let V be the volume of helium. In the balloon. Okay, and in inches cubed. And then R is the radius of the balloon in inches. Those are our key. So because we're talking about rate of change of volume, rate of change of radius, these are going to be our key quantities, volume and radius. So now we want to write an equation that relates to the quantities. Sometimes it just might be given to you. You might just have the equation that relates to those quantities. Other times you'll have to figure it out or apply what is appropriate. So we have the volume of the helium in the balloon and the radius of the balloon. And we need to come up with a relationship, the quantities equation. What is the quantities equation if we've got volume of helium in the balloon and radius? What will that be? I know these guys know, I know Aiden knows, I know Kyle knows. So what is that relationship? Here's my list. Uh-oh. Mark's got his list. Jacob Harvey. That's not you. Where's Jacob Harvey? He dropped a while ago. Okay. Ashley. Yeah. I know you just walked in. So we got the spherical balloon. We want to relate volume to radius. Do you remember what that is? She got it. She nailed it. So either you remember that or you look it up, right? This is going to be the relationship of the radius and volume of a sphere. Okay, radius and volume of a sphere, that's the relationship. Okay, then we're going to, what do we really need? We really need how the rate of change of volume and the rate of change of radius are related. So we derive it from this. Okay, and with respect to time, right? So this is we talked about last Wednesday, we did implicit differentiation. We're going to differentiate term by term, and now with respect to t, because it's about per minutes. So, rate of change of volume with respect to time. So you can either just say, so it's just v, so you can either just say dv dt, or if you want to think about it like the chain rule, you can think about, oh, well, it's going to be 1, rate of change of v is 1, then times the rate of change of volume, chain rule. So either way, you end up with dv dt. Okay, equals. So now we need to take the rate of change of this expression here with respect to time, right? With respect to time. So what is it? So we hold on to the constant. And with respect to time, we get, and remember that r is a function of time. So what do we have? We have a composite function there. We have a function of time cubed. So to do the rate of change, we do 3r squared, right? This is chain rule, right? 3r squared, exterior function with respect to the interior, times rate of change of the interior. So what do we have now? We have an equation that relates the rates. It brings together two different rates of change, the ones that we needed. So that's our related rates equation. Right? That's our equation that relates those two rates of change. Okay, and so then we figure out which one are we trying to find. It's asking for how fast is the radius changing? How fast is the radius changing? So what are we looking for there? How fast is the radius changing? That was our dr dt. That would be our dr dt. So that means if we're going to solve for that one, that means we need to somehow know everything else in the equation, either given or we'll have to figure it out. And then we can solve for dr dt. Okay, so let's go to the first thing, dv dt. Do we know it? We do. It's 150, right? Is it 150? It is not 150. What's happening to the volume? We're expelling. So the volume of the balloon is decreasing. And we know our key fact, if a quantity is decreasing, rate of change is negative. Remember that? We were taught on that. So watch out for that. So we got negative 150. Okay? And the only other thing left is r. Do we know what r is? It's not given directly, but if we're solving for drtts, there's got to be some way we can get it. There's got to be some way we can get it. So it's going to be times 3. So we're going to be able to get that somehow. And then times drdt, which we'll solve for. So how squared? How do we get the radius? How are we going to get the radius? Yes, sir?
Well, we know the volume for which we're looking for the rates at that point in time. So
right.
we just use the volume equation to
Right. So looking back here now, we know the volume is 500. This will allow us to solve for the radius corresponding to a volume of 500, and therefore the radius at the time when we need the rate. Okay? So what are we going to do? We're going to do 500 times 3 divided by 4 pi cube root. So a little side work over here. That radius is going to be the cube root of, what, 500 times 3 over 4 pi. Did I do the math right? And someone's got GC or a calculator open. Let's get a good approximation for that. One more decimal place. 4.9. Someone else get that? Just confirm it. Someone else get 4.92?
Yes.
Awesome.
Sir?
Yeah.
We could substitute square root to cube root as to the 1/3, right? Still.
Yep. Cube root is the same as power 1/3.
Just making sure.
That's right. Okay. And so now we've got that 4.92. Is that negative? And it's just a radius, right? It's not a rate, so it's just a radius, which would always be positive. Yeah, and we could, so this expression is exact. If you want to put this exact expression in there, that's fine, and maybe that's even better. But I think we have enough precision there to be okay to get a good approximation of dRdt. But if we really want to be technical, and we could put that cube root expression in here, okay? Put that cube root expression in here and round at the very end, okay? Round at the very end. Maybe that's better. Okay, so then, but this will be easier for now, a little quicker. So what's dRdt? It's going to be negative 150, times 3 divided by 4 pi. Well, those 3's go away, right? 3's go away. So negative 150 divided by 4 pi divided by our radius squared. And anybody got that? So dRdt then is negative 150 over 4 pi 4.92 squared. And we're going to get a negative value. Does it make sense? And why does it make sense? Right, radius is decreasing also, so the rate of change of radius is negative. Did you get it?
Yes, it's negative 0.49 inches per minute.
Did somebody else get that?
Yes.
Did you say it before and I didn't hear you? Or?
Oh, the first time you ever said it, you did it.
Okay, so about half an inch per minute at that moment, right? So at that moment, what the radius is shrinking about a half an inch a minute at that moment when the volume is 500 inches cubed. Okay, any questions on that example? Yes, sir.
So, like on the test, if it gives us like a sphere to do this with, do we have to memorize all the equations?
So you need to know basic ones, but a little more complicated things we'll give you. But you need to know the area of a square and the area of a circle and the perimeter of a rectangle and these kinds of things we would expect. But yeah, something more like this in this realm we would give you. Yep. Other questions? Okay, let's do one more of these. One more related rates. You got some for your homework. Last chance for questions on this one. Okay, so here's one. A motorboat leaves the shore going 28 kilometers per hour in a circular arc. So it leaves from here. It's going to start here. It's going to head this way. Okay? And the circular arc is 60 meters, okay, that it's turning. How fast is the boat's distance from the shore changing when the boat has traveled a distance of 150 meters around the circle? Okay? So what's the first thing we want to do? It's the first thing we want to do, remember? We want to, yeah, so our general idea here will be that we want to get the quantities equation, and we'll use implicit differentiation to get the related rates equation. All right, so we got to know, to start with, we got to know what rates are we relating. We want to start by identifying what rates we're going to relate, and then from those we get the associated quantities, and then we build the quantities equation. So then here's kind of an overview of the solution. Identify the rates involved, assign notation variables for the quantities and rates, Make your quantities equation, derive your related rates equation. Okay, so what are the rates involved here? 28 kilometers per hour. So let's write that down. Good. And before let's just talk about what that is. We won't assign notation, but what is that? 28 kilometers per hour is the rate of what? What is that a rate of? Yeah. Yeah, it's the speed of the boat. So anytime you have a speed of something, it's a rate of change of what quantity? Distance. So what distance we're really, speed it is a speed, but we want to figure out exactly what distance we're talking about there. Yeah. Oh, yeah. So it's arc distance, right? It's arc distance. If it's the speed of the boat, it's how fast the distance is changing around the arc. So we'll just keep that in mind, that this is like a change of arc length. So remember that a speed is always a rate of change of distance, and you have to visualize or imagine that distance. Okay? Don't just think of a point moving. Ask yourself what distance is changing. In this case, it's that blue arc length. It's that the rate of change of that growing. Okay? Always think of a speed as some distance changing, not a point moving. Okay, so what other rate do we have here? It says, how fast is the boat's distance from the shore changing? Okay, can you visualize what that is? So we got, this is rate number 1. And then this is the other rate. How fast the boat's distance from the shore. So can you imagine that distance? How would you explain or describe or see that distance? Yeah. Like in this picture here. Okay, that's the distance from the shore? Is that what you're going to say? The blue line is the distance from the shore. How fast is the boat's distance from the shore changing? Yeah. Yeah, so the distance to the shore of the boat, say at this moment, is this distance right here. It's straight down. It's like a vertical. In this picture, it's vertical, okay? So what do we want to call that? It's kind of like a y coordinate, right? Let's call it y. Okay? So now, arc length, what are we going to call arc length? We can call that, oftentimes they use S for arc length. So what rates, let's write down what the rates are first. So what rates are we wanting to relate here? What rates do we want to relate? Distance from the shore. So what would the notation for the rate be for distance from the shore? For the rate of change of distance from the shore, what would our notation be? What would our symbolism be? What is the distance from the shore? What is that? What have we called that? Y, right? Y is distance from the shore. In meters. Okay? So what's the rate of change of distance from the shore? How would we symbolically, yeah, dy dt. Okay? And then what's our other quantity that we have? S is the, arc length distance, or distance traveled by the boat in meters. And its rate would be ds dt. So what do we need here? We need an equation that brings together y and s so that we can derive an equation that brings together dy dt and ds dt. So we need an equation that relates y and s so we can relate dy dt and ds dt. Okay, so we're looking up at this picture here. We're imagining s increasing, and then this y changing, right? The distance y as s increases. What's going to bring together y and s? It's going to bring together this arc length distance and that vertical distance to the land. Aiden, what do you think? Mm-hmm. Okay, I think he's onto something. So hopefully, trigonometry, angle, came to mind here. So let's call this angle theta. Okay, and so that angle theta. So can we start by, so what did we define theta as? What is theta? Theta is, who remembers what we said last week? What is an angle theta? What is its meaning? Only Kyle? We did our crash course. Charlie? Number of radius lengths along the arc. Exactly right. Theta is the same as the number of radius lengths that this distance s meters is. Okay, so then can we write what theta is? Number of radius lengths, that's right, along the arc. So can we bring together theta and s? How would you express the number of radius lengths in terms of s, which is in meters, right? S is in meters. How many radius lengths is that? If you've gone s meters, how many radius lengths have you gone? Yeah. Right, you would take the total number of meters and you would divide by how many meters each radius was, right? And how many meters is each radius? 60. So it would be s, if you took s and broke it up into pieces of length 60, you'd get how many radius lengths you have. And that's what the angle theta is, s over 60. So that's right out of what we talked about, was it last Monday? In our crash course, right? Our crash course, we said an angle is simply a number of radius lengths of arc length, connecting the rays, right? Connecting the rays. All right, so if you go s meters and each radius is 60, then you're going to take s and break it up into chunks of 60 meters, and that'll be how many radius lengths? And that'll be your angle. Okay, good. What about y? So what does y have to do with? So how can we get y involved in the picture here? Yes, ma'am. Okay, what was sine theta? Let's write out what that is. So sine theta had to do with vertical distance. Sine theta is? That's not going to help us here. So we want to get to back to the basic meaning of sine theta. Who remembers what sine theta was? Everything was a number of radius lengths, right? Theta, cosine theta, and sine theta were all measuring something with the radius. What was sine theta measuring with the radius? Okay, that was measuring the vertical distance from the horizontal diameter in radius lengths. So this was the vertical distance from horizontal diameter. Again, in radius lengths. So that will be what? If it's in radius lengths, that'll be a fraction of a radius, right? Because the most number of radius lengths you could get would be 1 at the top of the circle. Anything else is going to be a fraction of a radius length. Okay? So now how can I write what sine theta is? So this right here, how can I write what? How many radius lengths that is. If it's y meters, if we're y meters up from the shoreline, how many radius lengths is that? So if we're y meters up, how many radius lengths up am I? That'll be sine theta. Aiden. No, I'm asking what sine theta is. I want to equate sine theta to something. Sine theta, if it's the vertical distance in radius lengths, how would I write what sine theta is? I know Kyle knows. I want to write this distance in radius lengths. Yeah. Is it y? So was y in radius lengths? No, y is in meters, but it has to do with y. So how can I use y meters to get how many radius lengths that is? Yeah, it's going to be y over 60 again, right? So if I have the number of meters and I want to know how many radius lengths, I'm just going to break that up. I want to take that fraction of one radius, right? So that fraction of one radius will give me how many radius lengths up I am. Okay, so so I've got some relationships here, and what do I need to do? I need to relate y and s. Because I want to relate dy dt and ds dt, I want to relate y and s. So we've got everything we need. How can I relate y and s? How can I relate y and s using these two things in the easiest possible way? So what do I kind of want to get rid of? Yeah, so I want to eliminate theta, and I know that theta is s over 60. So go ahead, Kyle. What is it? Yeah, so if my theta is s over 60, I can take sine of s over 60, and that equals y over 60. So there's my relating of the quantities y and s. So because we were talking about arc length, we couldn't just use the triangle formulas. We really had to go back to the core ideas or the core definitions of theta and sine theta to do this. Okay? So we've got sine of our angle, and our angle is our number of radius lengths around the arc, which is s meters around the arc over 60, equals then the vertical distance in radius length, or y over 60. And now what are we going to do? Find the related rates equation. Find the related rates equation. So what do? We're going to take rate of change with respect to time. So we got like a double chain rule going on here. In fact, it's a triple chain rule. Okay? So we got to do this right. Left side, rate of change. First, start with the exterior. Rate of change is cosine. So we're going to do cosine of s over 60 times rate of change to the inside. 1 over 60 times ds dt. Did you catch it? Okay? Equals rate of change of y over 60 with respect to t. 1 over 60 dy dt. Okay, so and then again, we're going to isolate which one are we trying to solve for, and then knowing that, then everything else we should be able to get. So what are we trying to find? How fast is the boat's distance from the shore changing? Which one is that in our equation here? That's dy dt. So we're trying to solve for this one. That means everything else we need to get some other way, and then we're going to solve for dy dt. So cosine of s over 60. Do we know s? What is it? 150, right? 150. S is 150. And then do we know ds dt? So you have cosine of, so 150 over 60. Is that 2.5? I'm putting 150 in for s right there. Okay, and simplifying, times 1 over 60, ds dt, 28. Oh, cool. So 2,800. Good catch. Equals 1/60 times what we're solving for. All right, make sure your calculator, so GC will always do radians. You'll have to do conversions to degrees. So if you're using GC, you don't have to worry, but if you're using a handheld, make sure you're in radians. Make sure you're in radians. Okay, we're going to do cosine. The 1/60ths can go away. We don't have to deal with those. Or got 1/60th in each side. Thank you. Kilometers 1,000, not 100. All right, so we need cosine 2.5 times 28,000. What do you get? Coming back up here to the top. Cosine 2.5 times 28,000, if I did all the math right. As soon as you get it, shout it out. Or sorry, just say it.
-22,432.02 meters per hour.
22,432. That would be meters. Right. Okay, which is, we can go back to kilometers, 22.4. Negative 22.4 kilometers per hour. Okay, we got another negative. Doesn't make sense. Doesn't make sense, and why? Does the negative make sense for this? Kilometers per hour. Because at that moment, with 2.5 radius lengths, you're over here on the second quadrant. Y is decreasing, right? You're getting closer to the shore. So this is how fast you're getting closer to the shore as you keep going around the arc at that moment. Negative 22.4 kilometers per hour. Okay, questions on this one? Yes, please. It's S. So that's the definition of theta. Theta is the number of arc lengths. Back from, remember, from 170? Yeah, so this is S. There's no 5, it's S. Does that clear it up? Okay. Other questions? Okay, so a really good problem that tests our knowledge of these basic trig ideas. We really got those. And then related rates. Last chance before we move on to something new. Yes, please. Uh-huh. Right, so this is a changing rate, right? So depending on where the boat is, yeah, right. So like at first, what's the rate of change from the distance going to do? It's going to increase rapidly. But up here at the top, what about the rate of change? Yeah, it's going to be 0, right? So for a moment at the top, that rate of change is going to be 0, and now that rate of change is going to be negative and getting more negative, right? Until down here, it's the fastest rate towards the shore. So it's a continually changing rate around that circle. Yep. Other questions? Okay, so that wraps up our examples for related rates. So now that we've done related rates and optimization, on the exam, it's not going to tell you which type of problem it is, so you have to identify. So what does it reference like a maximum or a minimum value? Then you know you're dealing with an optimization problem. Does it reference more than one rate of change? Then you know it's a related rate. So you got to read carefully, know what kind of problem you're solving. Okay. Last chance. Okay, so then the last part of the course is we're going to revisit the fundamental theorem and look at some, explore that further that we didn't do before. Okay, so we're going to return back to the fundamental theorem, which was kind of the big kind of pinnacle of the course. It was kind of mid-course, but we want to look at more aspects of that. think that is here. Yes. Okay, so let's just review rate of change and accumulation. In the first half of the course we looked at, you know how fast something is changing, you want to know how much of it you have. So here's a context. Okay, so over on the left we've got a rate of change of elevation as a function of distance from the coast. And that's in 100 feet per mile. And then over here we have an actual elevation graph that's associated with that rate of change. Okay? So rate of change of elevation as a function of distance from the coast, and then miles. Okay, so using the exact rate of change of elevation function r, write a function f that gives the exact accumulation of elevation starting from a miles to x miles from the border. So we want to start, so any place here. So say right here. We call that a. And I want to write an expression that gives me the net change in elevation starting from a to any so right here. So starting from a, okay, to any value x, I want to write an expression using the r function that gives me the net accumulation of elevation starting from a miles from the coast to x miles from the coast. Can you do it? Can you do it? See if you can do it. Everyone try. Okay, at this point it has nothing to do with E. Okay, nothing to do with E. It's just using that rate function. I want to write an exact net accumulation of elevation starting from A until X. Where's Lillian Dorice? Do you have an idea here? Okay, good. So if we've got rate of change and we want exact net accumulation, what should have gone off in your head was integral. That's our integral, right? So that's what that function f is. It's the integral from a to x of capital R t dt, and this capital R is representing an exact rate of change function. So so this is given exact rate, exact net accumulation. Okay, and how does this thing work? What does this remind us of? When we see integral, it should remind us of what? The long A equation, the complicated A equation that we worked on. That's what it reminds us of. Because it's still a sum, right? We're summing up. Greek, German S is sum of what? Summing up what? Many bits. And each bit is calculated by constant rate of change, m dx. Okay? So we're summing up many bits of change. Each one of those bits is by a little constant rate times a little change in x. And that we worked hard on that for a month, okay, to come up with this compact notation that reflected all those important ideas. Okay? Super important. All right, so now, new question. Suppose E is the elevation function. Now, how can F also be written in terms of E instead of R now? So it's the same A, starting at some A, and going out to some X, like this. How can you write that same function F in terms of E, if E is the elevation function? Are you Slade? No. Where's Kyle Slade? Kyle Slade here? How about Melissa, Imperial? Yeah. So can you also write the function f, the net accumulation from a to x, but now instead of using r, can you use function e to do it? But I want to use e, so I want to recap the f function in terms of the e function, which is like a total amount function. What's that? Not the rate of change. Not the rate of change. Yes, ma'am. No, I want to write f in terms of e. So f is the net. It's the net change of elevation, and e is elevation. So how would I write it? Yes, ma'am. That's right. It would be the final elevation, e of x, minus the initial elevation, e of a. Does everyone see that? Okay, so we've got two ways of writing the same thing. The accumulations of small changes in elevation, starting at a miles to x miles from the border, or what? That's the same as the total change in elevation from a to x miles from the border. So the left side is like an open form representing that process of summing up all the little bits of change. And then the right side would be, okay, we know the final elevation, we know the starting elevation, just total change, right? Total change is final minus initial. So this is, in essence, if you remember, this is in essence the fundamental theorem. The fundamental theorem says that the net change in amount modeled by f of x, that would be like our capital E function, as x changes from a to b, can be represented in two ways. We can represent it as final value minus initial value, or we can represent it as accumulation of many changes, each one computed by m dx. Okay? So like f of b minus f of a. Or the sum of all the accumulated changes at the rate r sub f, starting from a and ending at b. Okay? And since they're both expressing the same quantity of net change, they're equal. All right? They're equal. Okay? And so then it could be, so we dealt with it as a function, right? So that final x that we were talking about can vary, and so then it's a function. The net change is a function of where you stop accumulating, meaning our value x. Okay? So by starting at an integral at a, it forces a reset. Okay, so the net accumulation value is always 0 at x equals a. So your net accumulation will always be 0 where you start accumulating, your net accumulation. Okay, but in the total accumulation, there could have been some total amount that had already accumulated, and that's your f of a. Okay, so that amount or total accumulation, it doesn't necessarily equal 0. But the net accumulation will be 0 at a, right? So, but this is anything that had already accumulated when we got to a. Okay, so that's an overview of the fundamental theorem. Two ways to express the same thing. And what we saw with that was this fundamental theorem allowed us to take open form expressions of net accumulation and then write them this way so that we could write them in closed form. So we have time to do one example of that. So this was one of the big deals with the fundamental theorem was it allowed us to get closed form net accumulation functions where before we couldn't. We could only write them in integral form. So for instance, if I've got an amount function f of x, we learned from the mastery test that what is the rate of change of f? What would the rate of change of f be? We die for these, right? Now, 6x, y'all in chorus, 6x minus 1. So we said that when we found that rate of change, we not only learned that that was the rate of change of f, but we also learned something else. We learned that any time we get an open form accumulation function like this that has that rate, now we can write it in closed form. Can you do it? Do you remember doing this? Can you do it? Can you write the closed form of this net accumulation function that's written in open form. Can you write it in closed form now? Everybody try. 2 minutes left. What's the key? The key to doing that is the fundamental theorem. Munzer. Al-Shadi. Is Munzer here? David Lucero. What do you think? Or how would you get started?
So, first, since we already established that it is equal to f of x minus f of a, you
Right.
replace the f of x with the rule,
Okay,
which is the 3x squared minus
good.
and then you subtract it. Then you subtract f of a from that.
And what is FA in this case is?
F of 4.
Good. Right, so applying the fundamental theorem, we know this is going to equal, this open form accumulation, net accumulation is going to be the same as f of x minus f of 4. Final minus initial. What is f of x? 3x squared minus x. What's f of 4? Well, 3 times 4 squared minus 4. So if we want to simplify that, we could. 44, thank you. 3x squared minus x minus 44. So look, so knowing that that was the rate of change of that also now allows us to know that we can write this open form accumulation in closed form as 3x squared minus x minus 44. So on Wednesday we will pick up, we're going to keep working with the fundamental theorem and learn more about this stuff. Okay?